Okay. Morning. Do you have any question from last week? Lectures or tutorial? You want to ask? Please don't be shy. Question from last week? Hello. What? Okay, one thing about the working you need to show in the exam or answering the question. So when you write the step, make sure you write why you can, the reason you can do the step. Okay, either by definition or by laws or by proposition or theorem. So explain what you did so that your step will make sense. You don't need to write out the full sentence, but just say by something else, by some laws. Okay. Okay, any other questions? So next week we got a quiz and then midterm on the week 8. I think we will do it. Okay, so let's start then. Start this week lecture. Okay, so what we have covered the position logic. So you can write sentences that you can decide whether it's true or not. And then we introduce set so that you can use the set builder notation to 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 gather the elements you want into a set. Yeah, so we got a different set. For example, natural number, integers, real numbers, complex number. These one are just for numbers. And also other set that you are interested in, maybe classes of BSC 136. So between this set, we want to create a bridge between them. So today we are going to introduce functions. Okay. So given two sets, okay, we want to uh, define a function between them. Okay. So what's the function? So function f, okay, from A to B is an assignment. Okay. The assignment of exactly one B in B to every A. So given one element in A, every element in A, I have to give you one element in B. Exactly one. Okay. Then we write and it's gonna be. Okay. So or sometimes we call it mapping or transformation. Okay. For example, the map of the Earth. So you send the point on the Earth, every point on the Earth, and then send to uh, a paper. So this points on the paper, right? So you can draw the Earth on the paper. So you make a 3D set into a 2D set. Okay, so it's mapping. Okay, so there's some terminology. So if f is a function from A to B, okay, then we call A is the domain of f. Okay, then B is the codomain of f. Okay, so A is the domain, B is the codomain. So f takes every value in the domain and give you an element in the codomain. And then if F sends the element A to B, so we say that B is the image of A. Okay. And also A is the pre-image B. Okay. Depend on what object you're interested in. One is the image. So image is on the codomain. Pre-image is in the domain. Okay. And the range, the range of also image of F is the set of all images of element. Okay, so in the set builder notation, we can write FA. So this is the range is equal to B in B such that B equal to FA for some A in A. Okay. Okay. So also you can try and define Fs for X a subset of A. Okay. So you can look at the smaller subset or consider subset inside a domain and then look at the image. Okay. So for example of functions, we have a function from real numbers to real numbers where send x to x squared. Okay. So you give me x, I give you back x squared. So this is a function. And then two, also can have a function sending x to x cubed and x equal to. So these are functions because every element in the domain, I can give you another element in the codomain. Okay. So these functions are actually called the real value function. Why are they real value? Because they take value in real. Okay. It's codomain is the set of real numbers. Okay. We could also have an integer value function where we take the codomain to be discrete. Okay. So this function also have algebra properties. So just like the propositional logic and set theory, these we can put two operations on the functions. So consider function real value function. Okay. I think you also can define for integer. You can try define for integer value function. Okay. Wait, let me think. Okay. So f1 plus f2. So we can define the sum of function and the product of function. So the claim, okay. So the definition of these are also functions from the same domain and to the same domain. Okay. So how is it defined? So you need to tell me where f1 plus s2 send the x2. Okay. Right. So what's the natural way to define this? So f1 and f2 are function, right? So they can send x to somewhere else separately. Okay. So we could take f1x plus f2x. Okay. So the first one is a real number. The second one, where is my f2? The second one is also a real number. So you can add them together to get another real number. Okay, so this is how we define the sum of the function. How about the product of function? Okay, so what's the natural way to do it? Multiply them. Okay, yeah. So you apply the function separately and then you multiply the number together. Yes, that's right. Okay. Yeah. So this one maybe like looks trivial, but this one this explain what's the definition of the function. Okay. And then so for example, we can do the f plus g just now, where you get what do you get? You get x squared plus x cubed. Okay. How about fgx? You get x2 times x cubed. Okay. So it's again another function. Okay. So there are two important properties we want to examine on the function. First of all is the one-to-one property. So what's one-to-one? The function is one-to-one, or we call it an injection, or we call it injective. Okay. If only if fa equal to fb, it implies the pre-image are the same for all a and b in your domain. So let's say our function is from a to b. Okay. Okay. So for example, yeah. So for example, fx equal to s squared is not injective. Anyone know why? Ah,
Or you can easily from the Q and the negative
yeah,
to as is the pre-image.
yeah, correct. So to show that it is not injective, okay, so you need to show the negation of this statement. So if you use the De Morgan's law, the for all will become there's this, okay, there's this a b such that fa equals to fb, but a not equal to b. You just need to find one, then it's enough to show it's not injective. Yeah, like your friend said, there's a lot of them. So first we can say just consider f2 equal to 4, which is equal to f minus 2. Okay. Yeah. And then 2 and gx equal to s cubed is injective. Okay. So to show that G is ejective, we need to assume we need to start with FA equals GA equals to GB first. Okay. And then we want to prove that A equals to B. Right. So start from things GA equals to GB. We have A cube equals to B cube. Okay. So from here, how can we show that A equals to B? Any ideas? So if a cube of a number is equal, so what are the roots of the number is equal. So how to go from here to A equals to B? Give you maybe 2 minutes. Any idea how to show A cube equals B cube implies A equals B? Hmm? Cube root? Cube root ah? You mean cube root both sides? Hmm. And can you do that? Why can you do that? And why can you do that? Why can you just calculate? I think you can, but there's a reason. But the reason haven't covered yet. Any other try? Yeah, if you take cube root is often immediate, but why can you take cube root? Action. Any try before I say something else? Contra positive. So you mean
We can first assume that A isn't equal to B,
okay.
and then I don't know.
So if A is not equal to B, why is it A cube not equal to B cube? No idea. It's a good try. Can try. Yeah. So I also don't know. Okay, so I also don't know. But yesterday me and AIT student, we figure out another way using roots. But I will put it up on the lecture notes afterward, so you can read it. But my way is to suggest to show that G is increasing. And then it is indenting. Okay, so what's strictly increasing? So I will introduce the definition of strictly increasing now. And then from strictly increasing, you can show that it is 1-to-1. Okay, so the function that say is a function from any subset of R to any subset of R. Okay, is increasing. It's increasing if fx less than equal to f1 for x less than y. Okay, whenever x less than y, and it is strictly increasing if fx less than f1. Okay, for x less than y, and decreasing if fx greater or equal to f1, and strictly decreasing. Strictly greater than f1. Less than y. For every x than y in your domain. Okay. So the graph may be something like this, increasing. Actually increasing will be like that. And then decreasing will be like, and then strictly decreasing is like. Okay. So you can show that something is so you can show that strictly increasing or decreasing. Oh, sorry. So need to be strictly decreasing. Improve the algebraic function Suppose. Okay, you can show that S cube is actually strictly increasing. So maybe I show you why G is strictly increasing. So the claim is G is strictly increasing. So suppose, okay, so I break into two cases because real number behave differently in negative and positive with the inequalities. Suppose we look at the positive number, right? Okay. Then gx, which is x cubed, okay, x dot x dot x, is less than x dot y, less than x dot y, less than y dot y, which is y cubed, which is equal to gy. So if x less than y, then gx is strictly less than gy. Next, suppose 0 is consider the negative case. Okay, consider the negative case. Okay. Yeah. Okay. So then y is less than x. Okay, right. And then if you multiply x on both sides, you will swap the sign, right? Because you multiply a negative number. And then if you multiply again, you get a swap on the inequality again. Okay. So similarly, you do a few times, do for different terms. Okay, maybe you don't know what's the different terms. So the idea is like this. So we will want to get, so want to show, so I want to get, so I write out my goal first. So y cube greater than x squared get y. Okay, so just let me label this. So this part here is this part. Okay, so try and figure out part 2 and part 3. Right. Part 2 and 3. Okay, use the similar method. Try figure out part 2 and part 3. So you can get this chain of inequality. Yeah, so that to show that y cube is greater than y. Sorry, this one is a y. So that in both cases you will get g. Hey, did I do something wrong? Cube y cube. Oh no, okay, yeah, no. I just write a different way. Okay, yeah, gy is greater than gx or y greater than x. Okay, any question? Okay, then what next? So next, okay, so the image of f is always a subset of your codomain. So if your image of f coincide with your codomain, then we will say the function is onto. Okay, the function a to b is onto, or a surjection, or surjective. Okay. if and only if for every element in the codomain, I can find a pre-image. Understand? Okay. So for example, fx equal to x squared is not onto. Do you know why? Why fx equal to x squared is not onto? Ah, what number? 3. 3 have a square root, right? Square root 3, right? So you can take, I mean 3, right? 3 have a square root. But the idea is, right, you need to find one number that doesn't have a square root in real. Huh? Pi. Pi got? Pi, you can take square root pi. Yeah. Pi can, you can take square root pi. Irrational.
We have some active number, and we cannot get the free image in the area of real number. The V.
So because s squared is always positive, so you can't reach negative. So for example, there's no okay, for example, -1 is not in the image. Okay, right. The square root -1 is in C, not in. Okay, and another reason is s squared is always positive, so you cannot reach negative. Okay. Next, so gx is onto. Okay, so this means for every b in the codomain, we can find the pre-image, right? So what pre-image can we take? So G is what? To remind you, G is SQ. Okay. So what pre-image we can take? Take A equal to 1. Such that such that G A equals to B. What A we can take? Huh? Yes. So we can take cube root B such that G cube root B equals to cube root B cube. Okay. Yes, right. So if you want to show something is onto, you need to find the pre-image for every element in the column. Okay. So definition again. So if so the function, if the function is both onto and one-to-one, we will call it a bijection. Okay, or it's bijective. Bijection, a bijection. Okay, this is adjective, this is noun, and then a one-to-one correspondent is it is both one-to-one and onto. So for example, fx equal to x squared is not projective because it is not one-to-one. It is also not one-to. But gx is the x cubed function is projective because it's both one-to-one and one-to. Okay, so in summary, so we can look at this for example here. So something is one-to-one and not onto is because there's something in the core domain that doesn't have a pre-image. Doesn't have a pre-image. If it is one-to-one, but it's not onto, it's because there are two elements in the domain get sent to the same element in the core domain. Okay. A and D are different, but they both get sent to 2. So it's like 2 to 1. Okay. 2 to 1. So 1 to 1 is like 1, 1, 1 to 1. 1 to 1 and onto. So everyone gets sent to a different element in the codomain. And also every element in the codomain has a pre-image. You got an arrow. So 1, onto. So neither 1 to 1 and onto. So there's one element in the codomain doesn't have a pre-image. And also this A and C get sent to the same image. Not a function, okay? So why is it not a function? Because A gets sent to 2 and 4. So you cannot decide whether you want 2 or 4. So if you are a function, you cannot be one to many. Okay? One to many is not allowed. Not even allowed for a function. Okay? So you also can see that the image of F is a subset of your codomain, right? So not necessarily be the whole codomain, but it's a subset of codomain. Okay. Also what? Okay, to show that a function is injective, you first assume that fx equal to fy. Then you need to show that the pre-image is the same. To show that it is not injective, okay, you just need to take the negation, right? Negation. So you want to negate this sentence here. Okay. So what's the sentence here actually? So this is for every x, y, okay? If fx equal to fy, then that's for y. So it's like for every x, y, and then if ex, y, then okay, maybe you got then qxy. Okay, two sentences. So if you want to negate this sentence, what do you get? So you get this is a practice on propositional logic. So you get that this and so on. Such that how to negate implication conditional statement. So remember the P implies Q is logically equivalent to not P or Q. Right. So if you want to not P or Q, you use the De Morgan law, right? So you get Px and not Qx, which is this. So assume fx equal to xy, P, okay, and not Q, not equal. Okay. So combine everything you learn. To show that f is surjective, consider an arbitrary element in B. You want to find an element in A such that fx equal to y. If you an element in B, you find an pre-image that gets sent to. So if it is not surjective. You just need to find one element in B such that there's no pre-image that's sent to B. Okay. Okay. Okay, next. So, so since we have a bijection, it's 1-to-1, so we can go from A to B. Similarly, there's a natural way to go from B to A, okay, using this bijection. So let's start with F a bijection. Okay, so I put some notation here. So the notation would be A is injective. Okay, maybe I put it here. So notation. So I'll write this as an injection, and then this as a surjection. So I use a hook error for an injection because it's like a subset. So if it is inject inside B, so we can think of like B is like this, A is like this. Okay. So you inject, and then surject, and then I put a double-headed arrow so that you hit everyone in the B. So if it is 1-to-1 and 2, then I'll write like this. Okay. So let F be a bijection. So we will define the inverse function. Inverse function of F. Okay. So it's the function F inverse from B to A. Okay. So we want to define a function going backward. So meaning given any element in B, I need to give you an element in a unique element in A. Okay. So how should I define this? So is the function that assign to an element B in B the unique A in A such that A is the pre-image of B. Okay. So you give me B, okay, you give me B. How do I send you to A? I just take the pre-image of B under F. Because F is on 2, right? So if it's on 2, there's one element that there's one pre-image that gets sent to B. Okay, so I will write hence F equals B. Okay. So how do you find the A? The A is given by the onto ontoness, the surjectivity of F. Okay. Then we will say F is invertible. Okay. So for example, fx equal to x squared is not invertible. Okay. So it's not invertible, we cannot define the inverse. Why? Because f minus 2 equals to f2 is 4. So if I give you 4, should I send it back to 2 or minus 2? Okay. So there's an ambiguity here. Okay. But gx equal to x cubed is invertible. Okay. So yeah, so it's invertible. So remember how you find the inverse function. Did you still remember how to find an inverse function? No? No? Anyone still remember how to find the inverse function on the high school? Let gx equal to y, is it? Yes, and then x cube equal to y, and then you solve for x, and then you define your inverse function to be dx squared. Right? So what is this step doing? So this step is look at every element in your codomain. Okay, you go and find your pre-image, and then you set your inverse function to be the function that send the x to the pre-image. Okay, this is the definition of the inverse function. Okay, any question? Okay, if not, then we will break until 10 o'clock. Okay. Okay. Yeah.
And actually, it's an odd function.
Uh-huh.
So its graphic will, symmetry with the 0 point.
Yeah.
Yeah. So I just need to prove when x is bigger than 0
Okay.
and it's strictly increase.
Okay.
So if I want to, I have to way. The one way is derivative. I mean,
Okay. Yeah.
yeah. So when x is bigger than 0, it's always bigger than 0. So
Okay.
it's straight increasing.
Okay.
Or I send to that x1 is bigger than x2 and bigger than 0.
Uh-huh.
So I use gx1 minus gx2.
Yeah.
I just need to prove that this is always bigger than 0. So it's straightforward.
Yeah.
So gx1 minus gx2 is equal to x1 cube minus x2 cube, and it's equal to x1 minus x2, and multiply the x1 x1 square plus x1 x2 x1.
Yeah.
So it's always bigger than 0.
Yeah.
So it's real.
Yeah.
So I think that can prove that
It's strictly increasing.
it's real.
Okay. I think this will
Yeah.
this will
So I think it's a way to prove that.
yeah, this is another way. Yeah, this good. Yeah. Yeah.
This is a condition that
Yeah.
so this is why the domain or his
Yeah.
his domain in
Yeah.
R
Yeah.
is such as
Yeah.
this domain is
Okay. Huh? X. Give me X.
This Y domain is
Yeah.
very injective. His Y this 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 has
Mm-hmm.
just this functions.
Yeah. Okay. And then, what's your question?
It's the very injective.
Uh-huh.
Is condition.
Uh-huh.
Every Y
Uh-huh.
pointer R
Yeah.
or pointer is this functions domain.
Yeah.
I mean the a functions domain
Uh-huh.
not equal to R.
Not equal to R.
Yeah.
And then.
So this definition the domain is R or his just his functions domain.
So.
Mm.
So what's your question?
Which is his definition? Yeah.
No, this Y. This Y is the core domain.
Just this function. Just this injective domain. Not R.
What is R?
R.
Real numbers?
Yeah.
Real numbers.
Yeah.
But so so this okay. So so this injectivity okay not doesn't only work for R. You can work for any set. Okay, any set. So this side is called domain. This side is called core domain.
Yeah.
Okay. So this this Y here, okay, the Y here live in here in the core domain.
Oh.
Okay.
Just this is special injective domain, not all injective.
Yeah. What do you want to ask? Slowly.
I don't know how to express that.
Okay. No, that's okay. Try slowly. Uh-huh. So this Y live in the core domain. You know, okay. And then this X live in the domain. Okay. R is just one example. Okay. So every
So this domain is special. Point. Yeah.
This Y is a point. No, wait.
For example.
For example.
This function.
Yeah.
So this domain, this.
So I agree.
Yeah.
Uh-huh.
Is this or R?
Oh, okay. So your question is it the okay? These two I introduced the notation. So if you want to talk about this whole thing here, okay, not necessarily R, but this one is called the core domain. Okay, this one is called a domain. If just this, we call the range of R, range of F. Okay, right? Because this is only the F that can reach. right? So we call a range. This one, the whole thing we call codomain. The whole thing. The whole set. Okay, the whole set. The whole the whole whole. The whole set here we call the codomain. Okay. And then only the thing that you can draw is the range of. So what you draw is the range. Okay. Range of F. Okay. This one is range. This one is codomain. Okay. And then this Y here only need to check for range. Range. Okay. Not the whole codomain. Because it can be the case that this is injective but it's not onto. If it's not onto, then you cannot. You don't have pre-image.
But I think
You think?
就是
Yeah.
just for this example,
Uh-huh.
I know this is A,
Yeah.
this is R.
No. A. Wait. This is
This domain
this is not domain. This is range. Domain here. Usually we think of it here. Domain here. Domain is something here. Yeah.
codomain
Codomain is the whole thing here. This one is the range.
is range, but
Mm.
this function is just this.
Yeah.
But
So?
this domain is
Range. Yeah. So
not matter. It doesn't
doesn't matter. Okay.
doesn't matter.
Yeah. Okay.
I get the range.
Uh-huh. This is range. Okay.
But 就是 these two condition.
Uh-huh.
And this is both both the either this or this or
No, this one doesn't work. This one doesn't work. Doesn't work because you sometimes you cannot find something that map to everything in R. Because you see, there's nothing get mapped to here.
but
Just work.
max 最多 max
Yeah.
最多一个
Yeah.
also can zero.
Yeah. Also can zero. Yeah.
So if this just for just zero.
That's zero.
Yeah. So I think neither this or this or equal equations.
I think not equal. Because if there's nothing, then nothing to check. This one. Interconcept. Consequence. But doesn't make sense. Let me think. There's something. No. Okay. So this injection here, you need to start with element. You need to start with point in A first. Point in A. Yeah, point in A, not starting from point. So we start from domain, not starting from codomain. But you think that you start from codomain. Yeah, it start from domain. So, for example, this one here. So we start from here. Okay, we doesn't start from here. Your idea is like I start from here. Everything here must have something get sent to. Yeah. So this one is not the idea of injectivity. So if you want to say it is equivalent, Maybe you can, but not necessary. Not necessary. Yeah. Maybe you can. Yeah. Yeah, maximum. Yeah, you can. You can, but not necessary. Yeah, you can. You can. You can. Yeah. Okay. Yeah.
Okay.
You know. Okay. Huh? Yeah.
I missed the last lecture because I have with medical screen.
Oh.
And then I, some company told me that the last lecture can get that
Recording.
great.
Which paper?
The last we didn't get the
Oh, maybe you send me an email and then I help you take the photo and then send you. Yeah. Okay. You send me an email and then I will go and find it. And then I take the photo for you. Because they also return me the physical copy. You send me an email and then I look for your quiz. Okay. Okay, I think it's good that more people come and ask questions, but although maybe you find it very hard to keep practicing. Where I stop? Okay. Where do I stop? Okay. Yeah. Okay. So next, so there's another way to combine two functions together. So suppose we have g from A to B and f from B to C. Okay. Then we can consider the composition. Okay. So, okay. Oh, it might be of one here. What else? Okay. So the composition of functions f and g. There's no ambiguity here. There's only one way you can do it. Is you do if you go from A to B and then B to C. So we will define fg. So in order by fg, okay, is the function from A to B, defined by for every A in A. Okay. Similarly, okay. So similarly, you can apply G to A first, okay, and then you get something in B. Okay. Since you are in B now, you can apply F. Okay, so this is what F compose G. This is the function. Function, I give you a element in the domain, you give a element in the codomain. So this is the difference of the notation here. Okay. So this is a function, this is applying and applying here. Okay. So you want example? For example, just now we have this s square and s cube. We can combine these two because they are going from R to R and then R to R again. So if we consider F compose G, we will have R to R again. So what is this? So Fgx is equal to f of x squared, which is equal to f squared s cubed. S cube power 6. Okay. So you can see that this just now we introduced the sum, introduced the multiplication, and then now the composition, they are different, right? So they give different things. Okay, so theorem is how you check just now the inverse function you found is correct. So there's one way to check it. So let f to be an invertible function. Okay, then f inverse is the identity, and f inverse f is also the identity. So what's f inverse? Oh no, sorry. Where's the identity? And where id is the identity function that sends every element to itself. So identity function is like identity functions going from A to A such that identity x equal to x. Yeah. So how to check, for example, yeah, for example, just now we found the inverse for the g. Let's put it out here. So gx equal to x cubed, and then g inverse x equal to cube root x. Okay. So if we do g inverse, okay, we will get like g on cube root x, and then cube root x, which is x. Okay. So g inverse is a function that sends x to itself. So it's the identity function. So similarly, you can check for g inverse g. Okay. What you get is g inverse of s cube, and then cube root s cube, which is x. Okay. So both ways the identity function. Okay. Next. So next we have the graph. So what's the graph of a function? So last week we learned the ordered tuples. So the graph of f is the ordered pairs A and FA. Okay. Which is in AB. The Cartesian product of AB. Okay. So such that A is this. Okay. So for example, we look at the function from z to z, right? So also look at the x squared function. So let's do this. Okay, let me draw this. Okay, so let's label this guy as, and then this guy as 0, 1. This is 1, 0. And then this one 0, 1. Okay, and then keep going. So maybe sum. Okay, so if I want to find the ordered pairs for this function here, first I will have this 0, 0, 0, 0, 0, and then 1, 1, and then also minus 1, 1. Okay. Also 2, 4, and then minus 2, 4. Okay. And then 3, 9. 9 is maybe somewhere up here. Then minus 3. Okay. If you on the other hand consider the real function, real value function, also x to s cubed, then you will look at the continuous. Okay, so you have all the points inside the lattice, and then the graph will be something like this. Okay, so this is the graph. Okay. Yeah. What? Nothing. Okay. Okay. Next, introduce two maybe useful functions, special function for you. So one is the flow function. So the flow functions is draw like this. Okay. So it's like a half bracket. So when you put bracket here, it's a flow. Flow function is going from real to z. Okay. That assign to every x in R the largest integer that is less than or equal to x. The next one is the ceiling function. The ceiling. So you know, cap the number. So what's the ceiling? So it assigns to every real number the smallest integer that is greater or equal to x. Okay. For example, what is the floor of 6.5? What's the floor of 6.5? 6. Okay. What's the floor of 7.25? 7. So what's the ceiling of 6.6? 7. What's the ceiling of 7.25? 8. Yes, good. Okay. So ceiling, floor and ceiling functions satisfy some nice property. In particular, this one, you see, the scalar, you can bring it up. You can bring the minus scalar, the minus up. And also, if n is an integer, you can just move it up first and then do the computation on this. The leftover. In fact, you just need to know about the decimal one, right? Because you can move all the integer up. Okay. So you just need to do computation on the decimal places. Okay. Next, we will go into matrices. Hey, I want to know whether you guys have take calculus or linear algebra or not. No, nothing. How about the future course? Will you guys do calculus or linear? Huh? You think so? Okay. Okay, never mind. So today we will touch a bit on matrices. So a matrices is a rectangular array numbers. Okay. The matrix with m rows and n columns is called an n by n matrix. Okay. So like 1, 3, 2, 4, 7, 8, 9. And so this is a 3 by 3 matrices. Okay, so this is a 3 rows and then 3 columns. Okay, so one kind of matrix is interesting to study is square matrix. So a square matrix is a n by n matrix. Okay. So one useful notation you need to learn for this matrix is, so we can label every entry in this matrix. Okay. How do we label it? So the first entry will label by A11. Okay. Let's say we have an n by n matrix. And then the second label we label A12. And then until A1n. Okay, n columns. And then going down we have A21. And then up to all the way up to AM. And then here we got A22. And then the bottom row we have M2 and then keep going until AMN. And then you can notice if it is a square, the diagonal term here will be the II term. This is the feature of the matrix. So the ith row, is the 1 by n matrix. So it's like A1, AI1, AI2, up to AIN. And then the J column, okay, is the m by 1 matrix, which is AI, A1J, A2J, up to AMJ. So the AI element of the entry of A is the AIJ. So compactly, we can write A as AIJ. Look at AIJ. If you want to tell people the range, you could add at the side, say that I is going from 1 to m, and then j is going from 1 to n. Okay. So if you want to write in the code or somewhere, then matrix, this notation is how you tell the computer machine. Okay. So similarly, if you have two matrix, you can add them together. Okay. But you can only add the same size matrix. Okay, but because different size, you can't really define how to add them because there's some ambiguity to match up the entries. But if they are the same size, you just add them entry by entry. Okay, the sum of A and B. B of the B is the M matrix. Such that. So what is A and B? So element wise, it is Aij plus Bij. Okay. So for example, 1321 plus 6571, you get 7, 8, 9, 2. Okay. And then the next one. So you also can multiply two matrices together, but they have to be in the right size. So let F not A be an M cross A matrix. Okay, and B is the A cross N matrix. Okay, so we can define the products. A and B. Okay. So we write A dot B or AB, simply AB, is the what matrix is this? This is a M cross N matrix. Okay, matrix. Such that A dot B is the every entry is the row times the column. So what's this notation here? So this notation here is like you have a M by K, right, M by K, and then K by N. So you get a M by N. Okay, first of all. Second of all, how to get the first entry in your product? You take the first row, multiply the second row. So what do you mean by first row multiply second row? So you multiply each entries, okay, and then you add them up. Okay. So for example, let me give you an example. So 2, 4, 1, 2. So this is a 2 by 2 matrix. Okay, maybe just another. So what can I put here? Maybe I put 2 by 3 maybe. Okay, 2 by 3. So I get, so what do I put? I put 1, 0, 3, 0, 2, 1. And then I'll get a 2 by 3 matrix. Okay, because you just take the first and then the last one. So what do you get? So first entry you get 2 times 1 plus 4 times 0. The second entry you get 2 times 0 plus 4 times 2. The third entry, do you get, what do you get? You get 2 times 3 plus 4 times 1. I have no place to write, so add them up. 6 plus 4 is 10. 1 plus, how about the second row? 1 times 1 plus 2 times 0. What do you get? You get 1. The second one you get 4. The third one you get what? 5. Yes, that's right. Okay. Okay, you should notice some similarity here. Okay, so we can add them, we can multiply them. Just now we also do this the same as the function, right? So we can add them, add the function, we also can multiply the function. Okay, or composite. Actually, this multiply correspond to the composite. Okay, so there's some similarity here. So between the function and matrix. So some function can be expressed in terms of matrix, and then use matrix theory to study them, which is the linear algebra. Okay, so just now we introduced the identity function. Now we also have the identity matrix. So what's the identity matrix of order n? Is the n by n matrix. We write it as In. Okay. The short form will be using this Kronecker delta. What's this Kronecker delta? Is the entry would be 1 if I equals to j. Okay. And it is equal to 0 if I not equal to j. So for example, In will be looking like this. So 1 on the entries, 1 the diagonals, and then 0 on the other place. So for example, you have this I2 here. So I2 is equal to 1, 1, 0, 0. Okay. So similarly, we can define how a matrix is invertible. So a matrix, so just now we have function invertible, right? So now we got a matrix invertible. So a matrix is invertible if there's this another matrix. Okay. Okay, let's call this matrix A. And then we got a matrix A inverse such that A inverse is the identity matrix and A inverse A is the identity matrix. So this one is the left, this one is the right inverse, this is the left inverse. And then they coincide. And then this is called a inverse of A. So if you want to check something is the inverse matrix of the other or not, you just multiply them and then check whether it's the identity or not. Okay. So another useful operation on matrix is called the transpose. So you can take the transpose of a matrix. So what's the transpose is? So let's given n by n matrix again. So the transpose of A, usually we will write AT, A to the power T. Okay, is the n by n matrix. So you sort the column and row. Okay, such that A equals to AJI. Okay, so you sort the column and rows. So for example, maybe example will make this really clear. So example is if you want to swap, for example, 1, 2, 4, 3. Okay, if you swap this, you will get 1, 2, 4, 3. Okay. So you turn the row into column, turn the row. Okay, this is the transpose. Okay. So there's some matrix that this symmetry, which is the transpose is itself. So a square matrix A is called symmetric if A equals to A transpose. Okay. For example, the identity matrix is symmetric. Then because if you do transpose, you get back yourself. Okay. And also, you can write out other example of symmetric, unsymmetric matrix. Okay, for example, this guy here is symmetric. Okay. So if you learn linear algebra, symmetric function will have some nice property, especially for the eigenvalue thing. Eigenvalue, if you learn next time. Okay. So why do we learn matrix? So let's do some Boolean algebra on matrix. So let's consider this particular function here. So different what? Different cost, not cost, different degree has different matrix they're interested in. For example, if you are studying statistics, you're interested in matrix that has sum of column and rows to 1, okay? Because they are probabilities. So in this course, we look at this matrix here that has only 0 or 1 in the entries. Okay, so I call it a 0, 1 matrix. Okay, and then we recall the Boolean arithmetic. Remember the and or, and then also the intersection and union. Okay. So B1 and B2 is 1 only if B1 equal to B2 equal to 1 and 0 to 1. Okay. How about all? All is either one of them is 1. So B1 is 1 or B2 is 1. And 0 otherwise. Okay. So gonna do similar things again. So we can add two 0, 1 function together. So let A and B be the 0, 1 function. Okay. So you can imagine we can add them together. We can also multiply them together. Okay, but we introduce this two new function, the new definition here. So we define the join, the join of A and B, denoted by A or B. Okay, what's A or B? You just take the conjunction on every entry, and then you also can do the mid and the mid together. And then mid together such that Aij and Bij. Okay, so let's try some easy computation. So let's do this. Let's take the mid of these two matrices here. What do you get? What do you get on the first entry? 1 and 0. 0, 1, 0, 0. Yes. So how about you get this? How about you take the, what's this? Join. The join There's two matrices. What do you get? 1, 1, 1, 1. Yeah, good. Okay, and then we can define the Boolean product. Okay. So you also have to make sure that they have the right size so that you can multiply them together. So this is M by K. This one is a K by N. 0 to 1 matrix. 0 to 1 matrix. 0 to 1 matrix. Okay. Then the Boolean product of A and B, okay, denoted by A, circle B, circle dot B, okay, is defined to be, so entry wise is the row, okay, the row meet with the column, okay, the row meet with the column, and then you take the point of, okay, and then keep going on, and then until you get the last guy. Okay, so for example, let's do some examples so that you can have some practical hands-on. Okay, so the first one is I, 1, join with 1, and then meet, no, 1 meet with 1, and then join with 1, 1, 1, meet with 0. And the second one, you get 1 and 0, or 1 and then 0 and 1, or 1 and 0, and then 0 and 0, or 1 and 2. Okay, so what do you get? You get 1. Huh? What's the next one? 1, 0, 1. Yeah. So through matrix, right? You can do few. You can combine the what? Combine the calculation together. Okay. And then actually you can see matrix as a function, right? So if you have a m by n matrix, okay, it's actually a function from Rn to Rm. Meaning, for example, like 2, 3, 2, 4. Okay, so this is a 2 by 2 matrix. So it's a R2 to R2. So if you multiply a matrix here, okay, so this is a 2 by 2 matrix. This is a 2 by 1 matrix. So you get a 2 by 1 matrix here. So it's in R2. This one is in R2. Okay. Okay, maybe you will think that R2 is a tuple, right? This, right? It's a Cartesian product, right? So there's another way to write this R2, which is using this vector notation here. So if you do this, this matrix will send the 1, 2 vector to where 2 times 1, 6, plus 2, 8, and then 2 times 1, 6, 4, 8, 8, 10, 8, 10. So sends this 1, 2 matrix here to 8, 2. So it's like you process two what? Two equations together. Okay. So this is the advantage of matrix. So you can do the computation at one go. Okay. Any other question or not? Questions? Questions? Just now one student come to me, right? So he in fact he's okay to show this strictly increasing stuff. So he measure this qy minus gx is greater than 0. Okay, because we want to show gy greater than gx, right? Okay, maybe I use another color so that it will differentiate. So size 2. Right? Very hard to see. I'm gonna go up here so I can use one. Okay, so he said to show this is equivalent to showing this. Okay, that's true. So you can look at y cube is y cube minus s cube. Okay, to show this is greater than 0. So you'll notice that maybe you can factorize it out. So you get something like okay. So from here, it's easy to see it's greater than 0 because y squared is positive. Okay. So if both of them are positive, then the product is positive. And then s squared is also positive. And then since y is greater than x, so this is positive. So positive times positive is greater than positive. Yeah, yeah, you also can do it this way. I think this one also works for negative if not wrong. Mm. Yeah, this one, yeah. Actually, this factorization here, you also can use it to show this directly. So assume this is true, and then you check that when is this equal to 0. And then to check that this is equal to 0, the only way is for this to be 0, because the root of this polynomial is not in real when you check the discriminant. But I will write it out in the lecture notes later when I upload it. Any other questions? No. Right. Mm. No. Uh, no question? Okay. Any questions? No? Okay. No question mean you guys understand or not? Ah, no? No question? Okay, maybe we have a break and 5, 8, then we'll come back.
Oh, whether I can understand this the codomain is bigger than
Yeah.
domain.
Yeah.
It means 1, 2, 1. And there is no 2, 2, 1. And on 2 means it's smaller. Because here's a 2, 2.
Not necessarily, because I can also have not 1 to 1 here. So I can send these 2 to 3.
What's the
That's the one.
the key to the difference for the two? I'm not really understand that.
What do you mean?
I mean,
What would differentiate? Differentiate what? Differentiate what?
means there is
Why?
1-to-1.
Yeah, what's your question?
I
Slowly. Time.
Let me translate.
Yeah.
Sorry. The key I judge the function is 1-to-1 or not, just to say if they're A, B, 2. 2, 2.
Yeah.
And the key to judge this just like if they're something more.
And then what's your question? You say you judge the one.
Yeah.
And then
Judge this one.
Yeah.
Just to say if there's something more.
Okay.
It's more, it's not the
Yes. Yeah. How about 1-to-1?
1-to-1, if there appear A, B to 2.
Yeah.
It's not 1.
A, B to 3 or something.
No.
Yeah.
So I mean this the judge. It's 1-to-1.
Yeah.
Okay.
Yep. Yeah.
Easily understandable.
Yep.
J is the row.
Row, yeah.
I row
Yeah.
is the column.
Yeah.
So
Mm-hmm.
these two. 0,
Mm-hmm.
1,
Yeah.
0, 0.
Why?
Why this is 1, 0?
Then here is row is 0, 1.
0, 1, yes.
So 0 and 1, 1 and 0.
0 and 1 and 0.
Yeah.
So for this is 1, 1,
Yeah.
1, 0.
1, 1, 1, 0.
0.
Yes.
0, 1.
Yeah. Okay. It's the same as this. Do you have the previous?
Oh,
Okay. Yeah, okay. It's the same as the matrix multiplication. Yeah. 哦，这个东西呢？这个东西？啊哈，你要我解释什么？哪一个不明白？你不明白这个 set？
代表
这个 set 代表什么？还是这个代表？
这个东西，
这个东西代表？
地方看
这个的 definition 还记得吗？这个 definition 是 A1 union A2 union A3，然后 union 到 AN，所以你要拿 n 个东西才能可以。
所以就是
然后这个是 A1 到
intersect 到 AN，
所以就是最小的。
嗯。
那如果它是 infinity，
infinity 的话 ，infinity 怎么呢？你要这题还是你要这题？你要做这题的，
明白这个东西是要做，
不明白这个东西要做吗？我有写那个 definition，你们有看过吗？要查，我有写那个 definition 出来，因为我不可以莫名其妙给你一个东西没有讲过的，所以它是有一个 definition 在。有，我只是教你们自己把它写出来，但是我有写它是什么东西。这个，你看这个，所以我跟你说什么是两个有连在一起的，所以现在有 n 个东西有连在一起，就是 n 个东西，也，所以这个是什么？这个就是这个，所以你现在要看什么 infinity 哈？
如果是 infinity 的话，加到 infinity 啊。
对，加到 infinity，对，加 infinity，对，没有错。
这为什么？为什么？
你看这个很简单，因为你这个是哪一题？这个 A 啊，因为你看你的 A1 呢是 one，然后所以是2了。如果你 i fix 成1的话，这样你的这个 set 就有1、2、3、4、5、6，然后到完了。然后如果这个 i 是2的话，你是2、3、4、5、6这样咯。然后你现在你要 union 这全部东西起来，所以你的第一个 set 有1、2、3、4、5、6、7、8到100，然后第二个 set 有2、3、4、5、6、7、8到100，第三个 set 有3、4、5、6、7、8。如果你把这些 set 全部 union 起来，你就得到啊，对吧？那1到 infinity 不是 A1，你要写出来。没有，你要把 A1、A2、A3 写出来先，你写出来先，你才可以，不然你想象不到。你把 A1、A2、A3 写出来先，呀，你把 A1、A2、A3 写出来先。
这个很难懂，是吗？那个 symbol 有时
啊，听不很乱。
有时候觉得会很难懂，不
呀
然怎样我们总结出这种东西？
，OK。OK，所以你要拿他们的 union 嘛，对不对？
infinity
什么 infinity？infinity 不是一个号码啊，你不会写 infinity 进去啊。你看他都没有写 infinity 进去。但是我们只是说，你把这个全部 union 起来，你拿到
不大，
最大那个，最大那个是什么东西？有什么号码在？啊？
不是
没有，infinity 不是号码，infinity 不在里面。里面有什么东西？
I 什么？
里面有什么东西？如果你把这全部 union 起来，你得到什么？ 什么号码？什么号码是什么？你讲。
对吧？
没有 integer 有 negative，所以没有 integer。啊？什么？positive integer 对，positive 对对 positive integer 对。
那种是 A1
那 A1 contain 什么嘛？
contain positive。
因 A1
A1 就是
1
到全部嘛，啊，就是你要的东西不是吗？
因为这些全部都在 A1 里面，
啊，
它就把
也是可以这样子想，
哦，
也是可以这样子想，也是可以这样想，可以这样想。
如果我写这个错，
没有错啦，只是说有一个更直接的方法。
我想不出，
怎么会想不出呢？没有，你不是想不出，就是你没有去理解它
解不了，
啊。
理
理解
解不了，
你现在不是理解了没？
理解了吗？
就这样讲哎，OK，这样子我们的思维是这样：如果我们能够用之前讲过的东西，就是在这个题目里面所讲的东西来去回答他问题，我们会尽量这样回答。如果不能够回答，我们就放那个鸡再加咯，有没有？这样啊，比如像这个就不能够用那个这种方式来回答他咯，这样我们只能够嗯。所以你想哦，如果有什么东西是在所有的 set 里面啊，在一个 set，你觉得有什么东西在里面？为什么没有？
没有没？
啊，哦，没有没啊，好问题啊，怎么没有啊？啊，怎么没有？假设啦，假设有一个东西在里面啊，
中
啊，中间哦，中间选一个，你选一个试下，你选一下试下，
到这边是没有2，
啊，到这边没有2
3到这边就没有。
哦，
啊，所以他的 argument 可以 extend，就是说你选一个号码，我可以再选一个更远的 set。他选没有这个号码，这样他不在这一个，这样他就不在。
到 infinity，
所以你每一个号码都可以这样子 test，所以你 test 到完是没有什么号码的。
之前写出来看不清。
对对对对对对。
好是所有人都得
infin，对，呀，我现在只是叫你找哦，我没有叫你 prove 哦。如果要 prove 的话，要做我刚才讲的东西，就是你找一个号码，然后你要找另外一个 set 呀，所以我应该不会叫你们 prove 这种 infinity 的东西，所以至少你要会看到是什么东西就好了，你不用证明给我看。先呀，因为这门课时间太短了，学不了这样多。infinity 表什么写出来哦？A1 是什么？A2是什么？呀，对哦。呀，对呀，对呀，yes yes
这也是全部去
呀，
对，
有加零，我有加零，你去哪里？我有加零，所以如果你要讲到就是 non negative integer，
但是老师如
可以讲
果是真正 theory 的话，是不是没有零？
这是 theory 吗？看你从哪个方向啊，有些方向是有，有些方向没有
因为我看好像有些是没有。
啊，是没有，一开始是没有。
lecture 是没有
我讲的是有
老，师说的有，
在我课上面就有，也看个人行。Yeah，
这个比较看跟这个
不一样啊，不一样，不一样。这个两个我有另外 define 的。
分，
对对对对对，这个只是 set 罢了。set 罢了。
零
之间的号码没有，没有没有没有，就这两个号码吧，零跟 I 吧。这是 set，这是 set roster method 的 set notation。这个是 interval 不一样。interval 有 definition 啊。
这个
这个就是它 definition 咯。怎么？
这个
什么？你看这题目是什么？这题目是什么？这是括弧。这是 interval。interval 意思说我中间的号码的
0到
哎呀， 这是它的 definition 咯。
如果 interval 就可以放 infinity 了。
可以是因为我们如果一写 infinity 啊，我们就没有写这个括弧的，我们就肯定是写这个 open bracket，因为不是它不在这个，它不是号码，所以我们不可以放这个，因为没有一个号码是它，所以这个写出来只是说一直继续嘛。这个的意思是说，
我们可以直接放 natural。
你如果放一个 nature 那边就死在那边了，你懂的没懂？
我一句话不是
就停在那边了，就停在那个 end 吧。你什么意思？你讲把这个
可以 natural number 代替。
在这个嘛，对不对？但是如果你放一个 nature number，那个 n 加 e 有没有在里面呢？可是我要它在里面，你懂吗？你如果放一个 n 呢？
你可以包括
对，所以放一个 infinity 意思说就可以再继续，不是说有这个 infinity 的。
不是可以写零，
可以啊，
也是这样。
但是问题是01就是 a e 啊。
突然走不到
这01
可以了。
啊，可是
可以。如果你真的临时很紧张，就写01。
这种很 professional，但是我们写不出来。
所以这个也是那个。
有时候转不过来。
呀，对，没错。
这个真的
是时间费。
OK，还有怎么样？等下再来，等我讲一下。Hello。OK，Okay. Oh yeah, I forgot to mention about the bijection and the cardinality of set. So if you have a bijection between sets, actually you can compare their cardinality, right? So every element in the domain you can send to the codomain. So if you have bijection between two sets, actually their cardinality are the same. Okay. But you can't really use cardinality of set and deduce property on the function. Okay, you cannot say this set is very big and then this function must be if the codomain is greater than the domain, you can't say that. Okay, let me write now. Okay. So if you have a bijection between two sets, then the cardinality of the set will be the same. Okay, this one is how you find the how to compare the cardinality. But if B is greater than A, you cannot conclude that F is not necessarily if B is greater than, it's not necessarily what do I want to say? What do I want to say? Just now. Confused already. Let me think. So what I want to say is you can't use, okay, how to say? Okay, so okay, there are a few cases, right? So suppose B is greater than A. Okay, so your codomain is greater than A, then your F is definitely not on 2. right? Because you cannot reach all the B because it's not enough element to send to different B, right? Can get what I say or not? Okay, so for example, let's say F if F got three things, okay, S1, S2, S3, okay, and then you got maybe 4 or 5 things here, Y1, Y2, Y3, Y4, Y5, okay? So every element only got one chance only. You only can go to one place, okay? Then that means you can't reach all the elements here. But it doesn't imply that F must be doesn't imply that F must be 1-to-1. Okay. I also can send different xi to the same y, right? Okay. So I mean, you some of the 1-to-1 and onto you can deduce from the cardinality condition, but some you can. Okay, let's try do the tutorial question for today, and then we will start discussing at 11:30. 一个其中一个意义是，比如说你要解这个 解这个什么？你可以把这个问题当成一个矩阵的，可以吗？就变成这个 equation 了，就变成一个矩阵了。
他怎么解？他怎么解？
他怎么解呢？没有学过。
不是，我说在矩阵的，就是用
矩阵的话，矩阵怎么解呢？
对，
如果它是有一个答案的话，OK，这一个什么时候有答案？当这一个 matrix 是 invertible 的时候，
对，
就是 invertible 我讲过，刚才如果有一个，如果这个叫做这个叫做什么 W， 这个叫做 W， 这个叫做 B，A W 这个叫做 A，OK，如果它这个 invertible 的话，我就可以找到这个东西了，因为这个是另外一个矩阵嘛，矩阵乘这个的话，我会拿到2乘1的，对吧？这个是2乘2，这是2乘1，这个是2乘1，所以2乘2乘2乘1，我就拿到一个2乘1。对，所以矩阵还有一个好处就是，像我刚才说，这个矩阵其实是一个函数来的，说它是一个函数从一个多维的空间去另外一个多维的空间。当你这个函数涉及多维空间的时候，你的那个函数可以表达成一个矩阵，就是这个刚才我写的这个只是1乘1的，这个不是矩阵啊。但是如果这个方向是长这样啊 ，OK，这个我就可以写成一个矩阵是2，因为2乘一个 x， 我会拿到2x，所以我把一个函数写成一个矩阵，所以有些函数可以表达成矩阵。那如果你把函数写成矩阵，你函数你要每一个都跟我讲去哪里，每个去哪里，但是矩阵一下子告诉你全部东西。
行列式和矩阵是什么？
行列式是什么？
是现在就是它之前看过一些，好像有一种是那种斜着乘算了，我确实忘了是哪里，就是比如说。它有一种算法是这么斜的，我会这样讲。
等你找到你再跟我，你找到再跟我讲。所以矩阵就可以一次过做那个算法。 Hello. Okay. Yeah, I think you guys got a lot of questions regarding the domain and range and codomain. Okay. So let me spell it out very explicitly in this example. Okay. So let's consider a function from R to R, tending X to S squared. Okay. Since we already learned the graph, so if to sketch the graph should be something like this. Okay. And then what is the domain? Okay. So the domain of F is R. Okay. So this part is the domain. So what's the codomain? So the codomain of F is also R. So codomain here. So what's the range? F, okay. Okay, what's the range of f? From the picture, you can see that it is actually the number that is greater than equal to 0. Okay. So the range is the place where f takes value on, takes value on. Yeah, right. Okay. So why we introduce codomain and range? Because it is not necessarily that the because this is infinite, so infinite I cannot use cardinality. So it's not necessary that this set is equal to the codomain. Okay. So usually we have so usually the this one. So usually the range of f is a subset of the codomain. Okay, usually it's a subset. Okay, in this case, subset. If they are equal, then we call it a onto. So f is onto if it is single. Okay. So usually it's a subset. And this is the relation between this range codomain. Okay. 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 So what's the okay, let's look at the question. So 2.2.32, the question is, if A union B equal to C union B, is it the case that A equals to C? Okay, the answer is no. So I can take N union R and then Q union R. They are equal. The union are equal, but A not equal to C. How about if I change the union to intersection? Again, it's still wrong because I can take Z intersect with N and then N intersect with the rational, then I still get N. I get Z not equal to Q. So how about if both of them are true, then you can show that A is actually equal to C. Okay. So and next, ask you to show this formula here, the tree union formula, how you count the cardinality. So in the class, I introduced this theorem here. So you can use this theorem and apply inductively, and then to get the answer of the tree unions. By realizing this union is another set, then you can apply to this two set here, A union B, C. Or if you want to pick A union B, union C also can. Why? Because the union is associative. So if you do any left associative or right associative, is the same. Okay. 2.3.2, you have to decide whether it's a function or not. The first one is not a function because you define one number and then it goes to two number plus or minus. Not sure which one to put. B, okay, B is the square root and square plus 1. Yes. Okay. Yes, it is a function. Next one is 1 over n squared over 4. Okay, it's not a function. Why? Because if you put 2 and minus 2 in, you get 1 over 0. So it's undefined. Okay, so if you change your domain that takes away 2 and minus 2, then this function is defined. Okay. And then 2.3.8 is just testing whether you know the floor or ceiling or not. Floor and ceiling. 2.3.10. Okay, I include 11 together, just do it together. Check whether a function is 1-to-1 or 2. So this is a function between two finite set. Okay. So first one is 1-to-1 and not 2. Okay. The second one is not 1-to-1 and not on 2. Because not 1-to-1 is because two different things to the same thing. And then not on 2 is because A doesn't have a pre-match. C, not 1-to-1 because A and B get sent to D. Not on 2 is because A, B, C. Okay. Oh yeah, not A. This is D, right? Looks like A. Yeah, A doesn't have the pre-match. Okay. And then 2.3.22, show that something is a bijection. Okay, show that the function is a bijection. So first you show it's 1-to-1. Assume fx equal fy, show that x equal y. Surjective, for every y in the codomain, you need to find me a pre-match. Okay. Okay, next. So minus s squared plus 7, you already see that this is a variant of s squared, so it's not 1-to-1 and on 2. You can find 2 points that give the same number. And then it's not on 2. C is not on 2 because there's an asymptote here. No one can reach the 1. If you show algebraically also can set the function to be 1 and then find the pre-match, but you get a contradiction. D x to the power 5 plus 1 is 1-to-1 and on 2. So why is it 1-to-1? So you can show that f is strictly increasing. And then why is it on 2? You just find the pre-match, like how you find for the function sq. And then 2.3.34. Okay. So the question about this, the central question about this question is, if we know about the composite, can we deduce something on the individual function? So if the composite is on 2, can we say that f is on 2? Or can we say that g is on 2 as well? Okay. So what we prove here is the outer function is on 2 if the composite is on 2. If the composite is 1-to-1, then the inner one is 1-to-1. But the other one, we don't know what happened to them. Okay. So if you have a composite function, not just 2, maybe n of them, you will know the outermost one is on 2 if the composite is on 2. If the composite is 1-to-1, then the inner one must be 1-to-1. Okay. So this is very useful sometimes. If you want to show something is 1-to-1, you don't know how to show, but you can keep compose until you get 1-to-1 function. Then I know the original one is good. Yeah. Okay. This is the technique you can use here. Okay. So, but to prove it's not too hard if you just spell out the definition of onto, okay, and then find the right candidate for to prove that something is onto. Okay, for example, let us run through one of these. Okay. For example, we want to prove this. So if the composite is onto, then we show that f is onto. So to show that f is onto, you need to take every element in your codomain and then show that there's something in B that get mapped to C. So you start with any element in Y. You know that F compose G is onto, so you can go all the way back to A. So you can find some A such that FGX is equal to 1. But you know that gx live in B. Okay, then you just take gx as your element in B such that f applied to gx is 1. Okay. So f is 1, 2. Similarly, you can use similar argument. No, yeah. Yeah, to show 1 to 1 and then C. If F compose G is a bijection, then G is onto if and only if F is 1 to 1. So there's 2 directions here. If G is onto, then you can show that F is 1 to 1. If F is 1 to 1, then G is onto. Yeah, not too long argument, just spell out the definition. 2.6.2. Okay, so just to check whether you know how to add in the matrix up, add the individual term. And then 2.6.4 multiply. Okay, maybe I found some of you still cannot multiply properly. So this one multiply with this to get the first entry. And then the first row, second column, get the second. This one is the 2, 1 entry. Okay. How to get the 1, 3 entry? You get the first row to the third column. So this one will tell you which row, which column to multiply. For example, this 2, okay, let me write down. So this one is a A2, 3. So this one is 2, 3. So you need to take the second row, multiply the third column. Okay, so this is row, this is column. Tell you how to get this number here. Okay, and then what else? This one also multiply, check whether you know that. Okay, I include this, although this is the odd number question, I want to include this because if you learn matrix theory, you must at least know the 2 by 2 inverse. So the 2 by 2 inverse is you invert the diagonal, you swap the diagonal term, and then you put a minus the off diagonal one, and then divided by this magnitude 1 over AD minus BC, AD minus BC. To show that it is an inverse, just need to check by definition. Multiply from the right, you get identity. Multiply from the left, you also get identity. Okay, just some matrix computation. And then 2.6.21, I want to include this because this one tells you the power of induction. Okay. You can use induction to prove some property in the matrix theory. So, but in between, I think you need to have this lemma here. So if A, B, and A are invertible, then you can find the AB inverse, which is B inverse times A inverse. Okay. This one is also easy to check because you just need to do this, checking this computation here. Okay. And then 2.6.26 also checking whether you know how to compute or not. And then that's all. So you can see that there's wide range of tutorial question inside here. Some is to check your understanding towards the definition, and then the other is checking whether you know how to do the computation. So in the actual exam, we also have computation question and also have these applying theory questions. Okay. It's similar to the tutorial question. Okay. Okay, so make sure you know how to do these tutorial questions. Yeah. Any question on that? No. What? Okay, say what? Serious. Anything else you want me to run through? No. Okay, next week got a quiz. Can see you next week. Yeah. Yeah.